Betelgeuse or insect Jew, a red monster star on the verge. Bug Jew, a red Goliath star, is a galactic wonder. Assuming that you put it where the sun is, it would reach out to the circle of Jupiter. It's tremendous, it's truly temperamental, and it's going to detonate. Prepare for an infinite fiasco of never-before-seen scale. Betelgeuse, the red monster star on the edge of our universe, is conveying alarming messages through space. Stargazers have tracked down something profoundly disturbing about this monstrous object. Utilizing the James Webb Space Telescope, famous researcher Brian Cox has given an intense admonition. The question that continues to come up is, are we going to observe a cosmic explosion blast that will change the night sky for eternity? The mystery of Betelgeuse in the immeasurability of the universe. Stars are conceived, live, and pass on in astonishing ways. As of late, one star has grabbed the eye and worry of both stargazers and the general public. Betelgeuse, a red supermonster star in the heavenly body Orion. It is extraordinarily monstrous and old. Its extraordinary rosy variety and changing splendor have for some time been charming, yet ongoing occasions have uplifted interest in this enormous monster. As we find out more about Betelgeuse, we are very close to a potentially great event in its history. But what could these progressions in Scarab Juice mean? Are we seeing the start of an inestimable exhibition on an incredibly colossal scale? Scarab Juice's tremendous size and life cycle. Bug Jew is a heavenly monster, roughly multiple times bigger than our sun. Its size is nearly outside human ability to understand. Imagine a star so gigantic that if it supplanted our sun, its surface would reach out past Mars' circle, wrapping Mercury, Venus, Earth, and Mars. This monster size not only represents the actual greatness of Betelgeuse but also demonstrates its stage in the heavenly life cycle. As a red, very Goliath star, Scarab Juice is approaching an amazing finish, growing and cooling subsequent to depleting the hydrogen in its center and melding helium. The age and development of Creepy Crawly Juice. What might be said about Creepy Crawly Juice's age? This star is assessed to be between 8 and 8.5 million years old. While generally youthful in human terms, it is antiquated in heavenly terms. For millions of years, insect juice has gone through sensational changes, developing from a hot blue star to the red monster we notice today. It is presently in its last stage as a red very Goliath. Stars like insect juice change throughout their lives due to the progressing tensions of atomic combination and gravity. Another trademark that makes the phase of Betelgeuse stand out is its exceptional ruddy variety. Its red shade emerges from its cooler surface temperature contrasted with different stars like our sun. Brilliance changes and historical records. The sun's surface is around 5,500 Kelvin, while insect juice's surface is around 3,500 Kelvin. This cooler temperature permits insect juice to produce light at frequencies that make it seem red. Anyway, this tone is more than just an appearance. It uncovers information about the star's physical state and the cycles happening inside its immense, vaporous volume. The fact that Betelgeuse's tone has changed over time adds to its secret. Historical records from Roman and Chinese periods show that Creepy Crawly Jew was yellow close to 2,000 years ago. By the 9th century, Arabic stargazers noticed its red variety. This change over the course of mankind's history isn't only a historical reference. It connotes the star's evolution, the great diminishing event. Another interesting part of Bug Juice is its changing splendor. It is a semi-regular variable star, meaning its splendor vacillates intermittently. This cadence, diminishing and lighting up, has spellbound researchers and stargazers for hundreds of years. Regularly, Creepy Crawly Juice goes through a multi-day cycle and a more drawn-out 5-year cycle. As early as 1836, Sir John Herschel recorded these cycles, and native people's accounts might go back much further. Anyway, what really makes Scarab Juice baffling isn't simply its brilliance changes but their abnormality. Unlike many stars that fluctuate in brilliance regularly, Scarab Juice sometimes strays from this pattern, recommending perplexing and less understood processes inside its huge structure. Unforeseen perceptions and later advancements. As of late, cosmologists and stargazers were stunned to notice a sensational and startling change in Betelgeuse's appearance. This remarkable darkening has raised various different kinds of feedback. This is now known as the Great Diminishing. In late 2019, the red very monster Betelgeuse, one of the most brilliant stars in the night sky and a noticeable element of the star grouping Orion, began to diminish bafflingly. The star was darkening so quickly that it started losing its light at a pace of 0.01 sizes each day on average. By February 2020, it was at its dimmest. The time conundrum and observing challenges. Insect juice, which can typically be seen with the naked eye even in regions with significant light pollution, turned out to be much fainter. Even casual observers could see the difference. The time conundrum, however, complicates tracking Betelgeuse's activities. Since light takes such a long time to reach us, when we notice a star like Betelgeuse, we are not seeing it as it is now, but as it was in the past. For Betelgeuse, the light we see today left the star nearly 725 years ago. This delay makes anticipating and observing quick changes in its behavior difficult. Observations and investigations by researchers. The Betelgeuse darkening event highlighted the challenges of continuous sky observation and our limited understanding of the vast and strange domains of existence they occupy. Andrea Dupree, the deputy head of the Center for Astronomy at Harvard and Smithsonian, and her group closely observed Betelgeuse's divine show as part of a 3-year study to track changes in Betelgeuse's external atmosphere. They used the Hubble Space Telescope to observe the huge star. These observations provided new insights into how a variable star like Betelgeuse works. Variable stars consistently extend and contract, causing changes in their splendor. Specialists had the option to inspect the layers above Betelgeuse's surface, warmed in part by the star's whirling convection cells. Thanks to Hubble's aversion to bright light, further investigation of Hubble spectra taken at various times in 2019 and 2020 uncovered the development speeds in Betelgeuse's upper atmosphere, the discharge of material, and its results. The spectra were principally made of magnesium, showing that material was moving from Betelgeuse's surface into its climate at about 200,000 miles per hour. This hot, thick material eventually traveled thousands of miles away from Betelgeuse, forming the dust cloud that dimmed the star during the 3 months of the explosion. Dupree and her group estimated that about twice as much material as expected was shot out from Betelgeuse. This unexpected event raised critical questions about the processes occurring within Betelgeuse and its future. Researchers suggest that the extraordinary dimming was caused by a combination of 2 key factors: a large plume of gas expelled from the star and the subsequent formation of a dust cloud that partially obscured its light. This observation was monumental in understanding the life cycles of massive stars like Betelgeuse, as it provided a real-time glimpse into their complex dynamics. What comes next for Betelgeuse? The significant changes in Betelgeuse's brightness, coupled with its advanced stage in the stellar life cycle, suggest that the star is nearing a dramatic end. As a red supergiant, Betelgeuse is expected to go supernova. When this happens, it will unleash an explosion so bright that it could outshine the full moon in the night sky and be visible during the daytime. However, the timeline for this event is uncertain. It could occur tomorrow, or it might take another 100,000 years. The impending supernova raises both excitement and scientific intrigue, as such an event would offer humanity an unprecedented opportunity to study a stellar explosion up close. The cosmic significance of a supernova. When Betelgeuse eventually explodes, the supernova will have far-reaching implications for both the scientific community and humanity as a whole. The blast will release immense energy, scattering heavy elements like iron, gold, and uranium into space. These elements are critical for the formation of planets and life itself. In a way, Betelgeuse's death will contribute to the birth of new stars and planets, continuing the cosmic cycle of creation and destruction. Monitoring the giant star. Astronomers worldwide are closely monitoring Betelgeuse using advanced telescopes like the James Webb Space Telescope and Hubble Space Telescope. The data collected will not only help predict the star's fate, but also deepen our understanding of the life and death of massive stars. With each new observation, scientists uncover more about the enigmatic behavior of this colossal celestial body. Betelgeuse's southern side of the equator, while all stars lose mass throughout time, was particularly striking since it happened at a much quicker rate than the Sun's. Stargazers discussed whether this event could signal a looming supernova blast, given the extent of the mass release and the ensuing darkening. Being just about 725 light-years from Earth, Betelgeuse adds to the intrigue, as any such blast would be visible from Earth and offer a unique opportunity to observe a supernova up close. Hypotheses about Betelgeuse's future. The question remains, what does this dimming mean for Betelgeuse's future? Is it an indication of an impending supernova, or is it simply a one-time event in the star's long and complex life? Several hypotheses have been proposed to explain this rapid transformation. One popular hypothesis suggests it was a precursor stage in the supernova process, gaining traction due to the belief that Betelgeuse is nearing the end of its life. Another common theory posits that dust, possibly from the star itself, was obscuring our view. It is known that Betelgeuse and other red supergiants shed material, which could gather into a dust cloud thick enough to block the star's light. A third hypothesis examines how changes in the star's photosphere, the visible outer layer, could affect its apparent brightness. This puzzle was tackled using a combination of observational techniques and in-depth analysis. Observational findings. Spectroscopic investigations revealed that Betelgeuse's effective temperature dropped, suggesting the star might be dimming due to a large dark spot on its surface. The fact that Betelgeuse's temperature decreased by around 170 Kelvin at the time of the dimming supported this idea. This pointed to massive changes on the star's surface. The Hubble Space Telescope played a pivotal role in understanding this unusual event. Hubble's observations showed that the dimming of Betelgeuse was likely due to a large amount of hot matter being ejected into space. This material formed a dust cloud that obscured part of the star's surface, reducing the amount of light reaching Earth. The dust cloud was believed to consist of very hot plasma that erupted from a large convection cell on the star's surface. As this plasma traveled through Betelgeuse's hot atmosphere to cooler outer layers, it formed dust grains, creating a cloud that blocked light from about a quarter of the star's surface. Impact on understanding stellar evolution. The discovery that Betelgeuse was losing material at a much faster rate than previously thought led to the realization that this rapid mass loss could affect our understanding of stellar evolution, particularly in red supergiants. Comparisons with other supernovae, such as SN 1054 and SN 1987A, have provided valuable insights into how stars die and how new cosmic structures form. If Betelgeuse eventually becomes a supernova, it would create a spectacular light show visible from Earth. The explosion would be brighter than the moon and might even be seen during the day. Such an event would provide a unique opportunity to study the final stages of a massive star's life, the formation of cosmic structures, and the distribution of heavy elements across the universe. Role of red supergiants in stellar evolution. Red supergiants like Betelgeuse are critical to our understanding of stellar evolution. These stars represent the final stages of a massive star's life cycle before undergoing a supernova explosion. Their immense size and relatively short lifespans make them excellent laboratories for studying the end phases of stellar evolution. These stars have a tremendous impact on their surroundings. The energy they release in their final stages contributes to the synthesis of heavy elements, which are essential for the formation of planets and life as we know it. Nucleosynthesis and heavy element formation. The process of nucleosynthesis in red supergiants involves the fusion of lighter elements into heavier ones. During their lifetimes, these stars fuse hydrogen into helium and later helium into carbon and oxygen. When the star reaches the end of its life, it attempts to fuse even heavier elements, producing elements like iron and nickel. These heavy elements are then scattered into space during the supernova explosion. Implications for cosmic science. The death of a red supergiant and its subsequent supernova explosion has significant implications for cosmic science. When Betelgeuse eventually explodes, the heavy elements it has fused over its lifetime will be distributed into the universe. This distribution of elements plays a key role in the chemical evolution of the universe, influencing the formation of new stars, planetary systems, and the potential for life. By studying these processes, astronomers gain insights into the history of our universe and the conditions that led to the formation of solar systems and habitable planets. Observational techniques for supernova research. Understanding supernovae and their precursors involves a range of observational techniques. Telescopes observe various wavelengths of light, such as optical, ultraviolet, and X-rays, providing complementary information about these cosmic events. The James Webb Space Telescope, for example, has advanced our ability to observe distant and faint celestial objects, offering unprecedented details about the early stages of stellar evolution and supernovae. Ground-based telescopes also play a critical role, providing continuous monitoring and contributing to our understanding of variable stars and supernovae. Impact on star-forming regions. The explosion of a red supergiant like Betelgeuse has enormous effects on its surrounding star-forming regions. The shock waves from a supernova can trigger the formation of new stars by compressing nearby gas and dust. This process, known as triggered star formation, can lead to the creation of new stellar systems. In the aftermath of a supernova explosion, the interaction between the shock wave and the interstellar medium also contributes to the dynamics of the cosmic ecosystem, influencing the distribution of matter and energy throughout the galaxy.